special right triangles is that they kind of have everything you need to know about upper level trigonometry are dependent upon these two triangles. These two triangles give us a whole slew of information. And what's nice about them is that if you reuse the same premise each time with them, it becomes super, super easy. Quite honestly, what you're going to be required to have to do today is identify what is opposite an angle and solve a one-step equation. I know that asks a lot, but if it's the same thing over and over again, you're going to be decent at it. So what I want to start with is this. If I start with a square, what do you know about a square? We have four right angles. We have four sides that are the same. Okay. What do the diagonals do to the angles? What do the diagonals do to these? They bisect. Good. They bisect the angles, and the diagonals themselves get bisected because they're also congruent. And you get four right angles in the middle. If you bisect a 90-degree angle, what do you get? Good. You get 45s. Now, as you get into this then, what I want you to start to notice is that you actually have multiple isosceles right triangles. If you look at the larger, you'll see that you have everybody see how that's an isosceles right triangle? No. What happens here is that this is an isosceles right triangle. You've got your two sides that are the same, and you've got your base angles that are the same. And then obviously within this square, you've got another one that matches it. You've got four smaller ones on the interior and so on and so on. But I've always found that it's easier, it's easier to mess with just one of them and then build out of it as opposed to trying to show it all at once. So I'm going to redraw just this the singular right triangle. Not too bad. I'm just going to move this one down. Then we'll relabel it. So real fast, in what's called a 45-45-90, it's going to be shown to you in a couple of different methods. One of the methods that you'll know that you have this specific type of triangle is that it might just have one 45-degree angle. Because if it has one 45-degree angle and a 90, that means what does the other angle have? 45. Good. Sometimes it might just be shown to you with those, which means they both have to be. Sometimes it might be shown to you as this, which means if you have that, then what do you have for your base angles? Just wanted to show you how that works sometimes. They like to change things up on you just so you guys understand where they're coming from as far as which one you're working with. Now, if I pick a number really easy to work with, let's say this side length is 4. What does that make the other side length? 4. Good. Reason being that it's isosceles. Now, how do I figure out what the hypotenuse is going to be? What method am I going to use? That right there. Excellent. So that means I would write out that I have 4 squared plus 4 squared equals my hypotenuse squared. Which I'll just call C for it. Are you okay with that? Now, if I type that in my calculator, I get 16 plus 16, which is 32. And then how do you undo squaring? Good. What's that? So if I square root the square root of 32, what do you get? 4 root 2. Now, this is why using that calculator is going to be important. That calculator leaves your answers in what's called the simplified radical form. If you don't have that calculator, you're going to have to sit there and go, okay, the square root of 32 can break down into the square root of 16 times the square root of 2, which is 4 root 2. And that's fine, you can do that. I'm telling you all year, get that calculator because it does all this stuff for you. And I got kids in Algebra 2 that still use that calculator when they have radicals. So, excuse me. What do you, thanks, I'm glad you. Watch what happens if I change this from a 4 to an 8. If I change those sidelines to 8, I would have 8 squared plus 8 squared. You get 128. What's the square root of 128? No one knows? 8 root 2. Excuse me? About what? Change the numbers to 18. Right. Now here's the deal, though. What do you do then if this side is... Now what do you do to work backwards? You're right. You guys are right. You're right. So if I go 10, all right, good. I like what both of you guys just did that. So if I go this way, if I go this way, it'd be x squared plus x squared is 10 squared, which is perfect. Okay. What's x squared plus x squared? 2x squared. What's 10 squared? 100. Good. Now what do you do? Divide by 2, you get x squared is 50. Square root of it, and what do you get? You get 5 root 2. Now, you can do all that algebra going back and forth, which is not wrong. Or realize that there's actually a shortcut pattern to this. The shortcut pattern that occurs with these 45, 45, 90 triangles is the following. Every time that you have a 45, 45, 90, you're going to have what's opposite your 45. I'm going to call it as some value of x. Opposite my other 45, therefore, it has to be the exact same value of x because it's isosceles. Then opposite my 90 would be that value of x times the square root of 2. And what we get here is this thing that I like to call an algebraic jig. In machining or carpentry, you use a lot of times something called a jig when you don't, so that way you don't have to like remeasure something. For example, if I'm cutting banisters for a deck railing, on your deck, you probably, if you guys have a deck, you probably have a bunch of banisters holding up the railing so you don't fall off your deck and cut your head open. Whatever. Now, instead of sitting there and measuring out over and over again on those 2x2s to measure those out, I'm not going to sit there and remeasure 34.5 inches every single time. Mark it, cut it. Mark it, cut it. That takes too long. So what you do is you take a piece of wood, and I take it to another piece of wood, and I screw it right there, 34.5 inches off to the end. So that way when I take my 2x2s, I just slide it up, it hits the end of this spot, I cut it, chops off, slide the next one, cut it, slide the next one, cut it. It's quicker, it's easier to replicate the exact same measurement over and over and over and over again without having to do any remeasurements, reusing anything. You guys ever seen videos of people in like a car manufacturing plant? Where they have those big machines that they have all the bolts and stuff that are in the same position. They walk up, they go, zzz, and they take it out, they put bolts back in, they go back up, and the same thing over and over again. They're using a jig. They're using the same tool that's set to fit the same spot over and over and over again to make their lives easier. It's kind of the same premise here, but I'm doing it via algebra. Okay? Because I know that every single time I have this type of triangle, this 40, what I would call a 45, 45, 90 triangle, when I'm at a 45-degree angle, I am always looking at some value of x. Therefore, when I'm at the other 45-degree angle, I'm also looking at some value of x, which then means that if I'm across from the 90, I'm looking at some value of x times the square root of 2. And by using this jig, if you will, you're going to be able to replicate your other side lengths over and over quicker. There's nothing wrong with using Pythagorean theorem, every time, but understanding how these values work and how these things coincide with one another unlocks everything for trigonometry later on, because these ratios of these sides never change. 1, 1 root 2, x, x, x root 2, things like that. Okay? For example, if I go back to the idea where if across from a 45 was something of 6, using my algebra jig, that means that across from this 45-degree angle is equal to 6. So everywhere I see an x, what am I going to replace it with? 6. And those are my side lengths. Could I have done the Pythagorean theorem over and over again? Sure. Is this quicker? Yeah. Big time. So you have 45, 45, 90. And what I want you guys to do today, pretty much every time you see one of these, write this out. When you write that out, it forces you to know where things are going. Okay? And it works the same way if you happen to know that, what happens if you know across the 90? Across the 90 is 8. No root 2 next to it. But we already figured out earlier, weren't we? You guys did Pythagorean theorem, you did that right away. It was 2x squared would equal 64. You can find out and solve it. Okay? But here, if I use my algebra jig, I can do it much quicker. If I know that across from my 90 is equal to 8, which one of those do I set equal to 8? The bottom one that says across from the 90. Very good. I bet you it's the bottom one across from the 90. That's a one-step equation. X times the square root of 2 equals 8. How do you undo multiplying? Divide. So in your multi-view calculator, what you can do, you divide both sides by the square root of 2. And that means your value of x is, well, let me show you how it looks. In the multi-view calculator, fraction bar, 8 over square root 2. And look what it does. It gives you a simplified radical. It gives you the simplified radical, so there's less thinking involved here. Okay? You would have gotten the same result if you did your Pythagorean theorem. It would have worked, but this is quicker, isn't it? So I know then that value of x in this problem is equal to 4 root 2, which means everywhere I see an x, what do I put? 4 root 2. And I work backwards on it. These are super fast to work with when we set them up this way. Okay? They're super fast to work. It's the idea that, remember, every time you have this special right triangle, it's what the angle is looking at. And all you're doing is setting up, at most, one second. Okay? Let's see what we'll do. Let's say in this case here, well, first of all, what kind of triangle is it? It's a right triangle. More specifically, special. Which special right triangle is it? Isosceles, which makes it a 45, 45, 90. Okay. Across from what angle do you know? I know across from a 45. So I write out my jig. 45, 45, 90. Thanks, man. I try. So if I know that across from a 45 is the value of the square root of 3, that means everywhere I see an x, I'm going to put square root of 3. And now I have to figure out how do I type in my calculator if I can say the word, the square root of 3 times the square root of 3. Exactly, literally, just like that. Take a calculator and type in square root of 3 times square root of 2, and it will spit out square root of 6. So here you have root 3, and here you have root 6. That's what we're doing today, guys. Super fast stuff. Not terrible? All right, let's look at the other one. The other right triangle comes out of the other special right triangle comes from an equilateral triangle.
So this is another special?
Yes, sir. There's only 2 of them. So when you have an equilateral triangle, you therefore know that all the sides are the same. And what will all the angles measure?
60.
60. Good. So if I know that all my angles inside of this are going to be 60, when I draw what's called an altitude to the side opposite, it's perpendicular to it. And if you remember, the altitude of an equilateral triangle bisects the side that it hits. If I say that these sides are 2, what does that make both individual parts? 1. The altitude also bisects the angle that it was at. So if you bisect 60, what do you get? 30 is good. So what's created here is what we call a 30, 60, 90 triangle. We get a 30, 60, 90. And what we're going to do is this. I already gave it side lengths of 2, which meant across from the 90 was 2, across from the 30 was 1. How do I figure out what's across from the 60? It's the what? Is it though? Yeah. Nope. What about Pythagorean theorem? I got to use the Pythagorean theorem. I knew he wasn't telling me to shut up, because Lord knows I pop the floor with him. But that's besides. I used Pythagorean theorem to find that side length. Now, is that missing side length? Is it a hypotenuse or a leg? It's a leg. Good. So let me move this to a separate one real quick. So I'd have something squared plus 1 squared is 2 squared. What's 1 squared? What's 2 squared? I'm back to the 2-step equation. So what do I do first? Subtract the 1. Good. So I get x squared is 3. Then what do I do? No, I'm not dividing. Square root. So x is the square root of 3. Okay. Now, same thing's going to happen here. No matter what, when I have this, what's called a 30, 60, 90 triangle, I'm always going to have the ratios of the sides as this, 1, root 3, and 2. Which means there's always going to be some multiplier of x within them. So you get another algebraic jig. We get another jig out of this, and I'll write it on both spots. In the 30, 60, 90, you get those patterns. We get those patterns. Which then will allow us to solve for problems if I know just across from one of them. And it doesn't matter which one I know, because then I can figure out what x is and simplify it through each piece. For example, if I go back to my diagram, and I say across from my 90 is 14. If I know that across from the 90-degree angle is 14, then I know that in my algebraic jig, which part do I set equal to 14? The 2x. Very good. So I know that opposite my 90 is 14. So I know that my 90 is looking at some value of 2 times something. Well, in that case, it equals 14. What is x? 7. Which means everywhere I see an x in the rest of my jig, what do I put? 7. Sir?
Is that the formula that we use for every year?
If it's a 30, 60, 90, you use that one. If it's a 45, 45, 90, you use this one. There are 2 formats to these, and that's all there is. And these never change. You will be using this regularly for most of the rest of the semester, as well as next year when you get to trig in Algebra 2, the entire what's called unit circle is built off of these 2 triangles. And if you understand what is opposite you in terms of values of x and 1s and 2s and things like that, it means placing things into space very, very easy. Yes, sir? Yes, you can. It still works. It's a little bit tougher with the equilateral triangle, but if you remember that opposite the 30, you always double it to get opposite the 90 because it was bisected. That's really the only weird part. I mean, this one you can go backwards in and out with the Pythagorean theorem easily because it's just the same value. That one's a little bit tricky. Same thing happens here if I change this up. Let's say I know across from my 60 is 9. If across from the value of 60 happens to be 9. Well, where do I throw the 9 in my algebra jig? Across from what? Try again, 3rd time's a charm. 60, very good. I have to throw it across from the 60 because where is the 9 located? Across from the 60. That's what we're doing here. It's a visual. You draw it and see where it's looking at. The 60 is looking at a value of 9. Which means, according to the algebra jig, I set x times the square root of 3 equal to 9. And it gives me a 1-step equation. Come back later. What's that? It's from Animal House. Come back later and do the dishes. So how do you solve for x? What do I divide by? Which is it? No. How do I solve that equation? I divide by the square root of 3. In your calculator, you take 9 and you divide it by the square root of 3. So you type in 9 over, you got it, over root 3 and hit enter. You get 3 root 3, which means that's the value of x. So if I know that the value of x is 3 root 3, everywhere I see an x in the rest of the problem, what do I put? 3 root 3. So across from the 30 is 3 root 3. Here it'll be 2 times 3 root 3, which is 6 root 3. It is quite literally that specific. Such a generic setup. Well, sure. All right? It never changes. It's a matter of what triangle are you working with. Write out the jig and solve for x. Okay. Let me show you an example so you don't have to keep drawing these. I made a sheet of a whole bunch of examples. These are examples so you don't have to keep rewriting them. Are you figuring out the shortcut? Oh, okay. So we knew that across from the 60 was that value. You need one? You know across from the 6, you need 2? Sorry. So since you know that across from that is 9, how do you undo multiply by root 3? Divide by root 3. Let's forget that x value. Just fill it in. So as I'm going through this, if I look at the very first question, what kind of a triangle is it? Okay, which of the 2 special right triangles is it? So it's the 45. I'll get it from you in a minute. So if I know that's going to be the 45, what I do is this. I write down my jig for the 45 first, and I fill it in. I do that right away. For every problem that I ever see, 45s or 30s and 60s, I'm always going to do the same setup. I'm always going to write out my algebraic jig because that never changes, ever. So that way you can math it easier. So as I go through the jig then, I know that across from 45 is some value of x, some value of x, some value of x times the square root of 2. Well, in my diagram, across from what angle on number 1 do you know? And I know across from 45 it is equal to 7 root 2 over 2, which means everywhere I see an x, what do I write? I write that junk down. That junk has to be 7 root 2 over 2. And the only weird one you have to worry about is the last one. 7 root 2 over 2 times the square root of 2. Which means you literally type it into your calculator how it's written. Yes, sir. Because that's the value of x. This value of x is 7 root 2 over 2. So I'm putting it here, which gives me this. See where I'm going with that now? Yeah. That's the reason why I use these jigs, because it never changes. So when you get 7 root 2 over 2 times root 2, what do you get? 7. Good. It's that simple. Look at number 3 directly below it. Look at number 3 directly below it. What kind of a triangle is it? It's a 30-60. Good. So the first thing I do on number 3 is I write down 30, 60, 90. I fill in the blanks. Psst, put it away. I write down my blanks. And then I know across from which angle? The 60. So I set equal to the x times the square root of 3, in this case, 5 root 3. How do you undo multiplying by the square root of 3? You divide by the square root of 3. Which means in this case, x is going to equal 5. So in the other two parts, everywhere I see an x, what do I put? 5. Yeah, Joe? Because the value of x is 5. Everywhere I see an x, I'm replacing it with 5. Nope, because I did that already. Yeah, Joe? Yeah. What we did here, Joe, is this. We know that across from the 60 is some value of x times the square root of 3. In that diagram, this value equals 5 root 3. We need to solve for x. That's why I divide by the root 3, which tells me that the value of x with this diagram is 5. Therefore, everywhere else I see a value of x, I replace it, I substitute in a 5. It's the same thing each and every time. Write out the jig, fill in what you know. What do you know across from? Skip over to 9. 9 is another 30, 60, 90. Across from the 30, some value of x. Across from the 60, some value of x times the square root of 3. Across from the 90, some value of 2 times x. Across from which angle do you know in number 9? The 30. Which means that the value of x has to be set equal to 2 root 6. Which therefore means everywhere I see an x in the other two parts, I'm going to substitute in 2 root 6. So that means this is going to equal 2 root 6 times the root 3. This is going to equal 2 times the 2 root 6. All I'm doing is replacing x with 2 root 6. I press buttons on my calculator, and it gives me my answer. This becomes no-brainer work if you use this jig over and over again. It makes this so much easier than anything else. So if I do this one, you get 6 root 2, I believe, for that. And if you do the other one, you get 4 root 6. Finish this. Write out the jig. Do that for all of them, okay? Write out the jigs like I'm doing and solve them through. It's the easiest, most efficient way to do these. Okay? You got what, 6 left to do? 7 maybe? But, yeah. Just write it out every single time, because eventually this will allow us to take a 30, 60, 90 next to another 45, 45, 90, which is next to a different 90, and so on and so forth. You can go all the way around a bunch of diagrams. Okay? You're just doing the same thing over and over again. Okay? Yes, sir. What's up in the back? Simplified radical form, no such thing as a decimal.